Hey guys, in this video I want to talk about Le Chatelier's principle. Now I know that we've been talking about Le Chatelier a little bit here and there in each unit. So we talked about in electrochem, if we're adding or removing a reactant or product, what happens to the reaction, or in thermochem, how if I increase or decrease the temperature, what that does to the reaction as well. How does it shift it? We're going to touch on those and go a little bit deeper, and then we're going to add a few more things as well. So this is very easy to get points in the multiple choice. They might even ask it on free response where you have to justify and things like that, but it's usually like a 1 point question kind of thing. Most of the time when you see it is on multiple choice, but it can definitely appear on free response as well. So let's start with adding or removing something in my reaction. We've talked about this in electrochem already. So I'm going to see if I can write over to the side here. Yeah, we have A plus B goes to C plus D for my reaction. And so let's say I were to add A. How will that cause a reaction change, or how will my reaction shift? Well, anytime I add something, I'm going to always shift away from that addition. So in this case, in this scenario, it would favor my products because the arrow is pointing towards my products. So I'm shifting right or shifting to favor my products. I actually like that explanation a little bit better. If I were to take A and remove it, however, okay, so let's say instead of, do a new scenario, and I want to decrease the amount of A or remove A, then my reaction is going to shift towards that decrease. So, hopefully this brings back some memories from electrochem. Now there's one addition I want to make to this. We have to be careful about what we're adding or removing. If you remember from our beginning discussion about equilibrium, is that if I have a pure solid or a pure liquid, I do not include those into my equilibrium expression. Because I do not include pure solids or pure liquids in my equilibrium expression, then if I add or remove a pure solid or a pure liquid, it has no effect on a shift. So let's say A here was a solid. Well, if the question says that I add A or that I remove A, then there will be no shift at all. And our justification as to why is because A is a solid and pure solids and pure liquids are not included in K expressions. So we have to watch out for that. So solids and liquids, no effect. All right. But if I'm adding or removing a gas or an aqueous substance, then it will have an effect. And if I increase, I shift away. If I decrease, I shift towards. So I want to skip this increasing pressure. I want to do that very last because this is a new one. If I add a catalyst, all right, there is no effect on K. It just makes my equilibrium happen faster. Remember, a catalyst, the only thing that it alters is activation energy. So it lowers activation energy. It does not change anything else. So adding a catalyst will have no effect. Also, inert gases, INERT, fall in this category. So inert gases will have no effect as well. Now let's move to changing temperature. We talked about this one as well during our thermo unit. Now, when we're changing the temperature, this is the only time when K can change. All right. Only time when K changes is when you're changing temperature. So not only will you have to predict a shift here, but you'll also have to predict whether or not your reaction is, not your reaction, but your K value is increasing or decreasing. So when we're looking at temperature, we first have to figure out, is it endothermic or is it exothermic? Endothermic reactions get positive delta H values. So when we write our reaction, we have heat in the reactant side. So if I increase my temperature, I'm increasing the heat here. And if I increase the temperature, much like when I was increasing or decreasing a reactant or product, if I increase, I shift away from that increase. Well, in this scenario, since it's endothermic, that means heat's a reactant. If I shift away and favor the products, what I'm doing, think about how K is calculated. It's products over reactants. So if I'm shifting to make more of these products, what's going to happen to K? Well, K is going to increase. So anytime a temperature change causes a shift to the product side, then my K value will increase because I'm making more products. Now again, only temperature can change K. Let's see if we were to actually decrease this temperature. Because it's endothermic, if I were to decrease temperature, my reaction will shift towards the decrease. So in this scenario, if a temperature change is causing my reaction to shift to the reactant side, then my K value will actually decrease. Reason being is because now I've made more reactants than I have products. And if I have more reactants than I have products, this K value is going to get smaller. So that's why K decreases. Now for exothermic reactions, those get negative delta H values, and heat is on the product side. So what happens if I increase temperature? Well, if I increase temperature, I shift away to favor reactants. And if I'm favoring reactants, my K value decreases. If I were to remove temperature, or decrease temperature, I should say, not remove. If I were to decrease temperature, then my reaction will shift towards that decrease. And if a temperature change is causing my reaction to shift to the products, then that means that the K will increase. So just a little bit of extension of what we've dealt with before. Now this very last one, increasing pressure. When we're increasing pressure, we also have to think about volume. So the relationship between volume and pressure is as volume decreases, pressure increases. So whenever we are talking about things that can be pressurized, we're looking at moles of gas only. So when we're talking about pressure or volume change, we're dealing with gases only. So let me write that Haber process up here. I'm going to write it in red off to the side. So that Haber process, if you remember, is the production of ammonia. So it's N2 plus H2 yields NH3. And there needs to be a 2 here and a 3 here in order to balance that. All of these guys right here are gases. All right, so gases for all of these products and reactants. So let's say what we're doing is we are either decreasing volume or we are increasing pressure to this whole system. We're kind of squeezing it tight, increasing the pressure, making more collisions to the walls of the container happen. The way that your reaction is going to shift is to the side where there's less moles of gas. Less moles of gas. So we have to figure out how many moles of gas we have on each side. And to figure that out, we just look at our coefficients. So for the reactant side, I have 3 plus 1, so 4 moles of gas. For the products, I have 2 moles of gas. So if my pressure increases, my reaction is going to shift to the products because there's less moles of gas residing there. Basically, I have more space, all right? If my pressure decreases, then I'm going to move to the side where there's more moles of gas. So in this scenario, I would actually transition or shift to the reactant side if there was more moles of gas there if I decrease my pressure. Okay, so when you're working with pressure, I have to look at moles of gas because that's the only thing that can be pressurized. And if I increase pressure, I move to the least moles of gas side. And that could be either side there. So let's go through some example problems to make sure that you guys are understanding this concept. So let me scroll down and we will get to that first example problem. So right here we have AS4O6 plus 6C yields AS4 plus 6CO. And we want to predict which direction that the reaction will shift if we have these scenarios happening. So the first one is the addition of carbon monoxide. So carbon monoxide's here. I make sure what state of matter it is. It's a gas. So that means it will alter or it will cause a shift. So if I increase that, I'm adding more, my reaction will shift towards the reactant side. And so I will shift left in that scenario to favor my reactants. Now, they could also ask this question in terms of what's going to happen to the concentrations or the values or the masses of AS4O6 or 6C. So they can ask what's going to happen to those. Well, anytime my reaction is shifting towards these species, then that means those values are going to increase in value. I'm making more of those. If my reaction is shifting away, then that means that stuff is going to decrease in value. So for this scenario, if I add CO, because my reaction is going to shift to the reactant side, AS4O6 and carbon is going to increase in value, and AS4, this product right here, is going to decrease in value. Let's look at part B, addition or removal of carbon tetra arsenic hexoxide. That's the AS4O6. So if I add or remove that, if I look here, then that is a solid. If I add or remove a pure solid or pure liquid, there's no effect. So there's not going to be an effect here. For part C, it says I'm removing AS4. So if I remove that, my reaction is going to shift to compensate for that towards the products. What does that mean about CO? Well, that means I'm going to make more of it. What does that mean about carbon and the tetra arsenic hexoxide? That means that I'm going to decrease its value. I'm going to use it up to make this stuff. Let's go to the next scenario, the next set of questions. This set of questions is dealing with the pressure. And how I know that is because it's talking about the volume. So it's saying that volume is reduced. What that means is that pressure is going to increase. And remember, when pressure increases, I always move to the side of the reaction that has less moles of gas. So we look here and we have 6 moles of gas on the reactant side, and we have 0 moles of gas on the product side. So I'm going to shift towards my products for that case. For part B, we have 2 moles of gas on my reactant side and 1 mole of gas on my product side. So we're going to move to the side where there's less moles of gas. So that will be the products here as well. For this scenario, we have 3 plus 1, so 4 moles of gas on this side, and we have 1 plus 3, 4 moles of gas on this side. Oh, well, we don't have a side where there's less moles of gas. So guess what's going to happen here? We're going to have no shift for this scenario. Let's now look at the last example problem, and it is discussing Le Chatelier in terms of temperature. And what we want to do is predict what will happen to K. So it says temperature is increased here. So what we do, we first figure out if it's endo or exothermic. So this is a positive delta H, so that means it's endothermic, and endothermic has heat as a reactant. So if I increase temperature, what is that going to do? It's going to cause my products to be favored. And if my products are favored, K is going to increase. For part B, this value is negative, so delta H is negative. That means that the reaction is exothermic, so heat is going to be a product. Well, if I increase temperature, my reaction will shift towards my reactants. And if that's the case, then my K value will decrease. So I hope these example problems help put Le Chatelier's principle together. And these are easy points to work with. So I hope that you guys do well with that.